let's launch into Jim's presentation. And Jim is going to be talking to us today about fault-tolerant parsing and the L1 markup language. So please join me in welcoming Jim. Thank you, Jim.
Okay, I'll try to share my screen here. Okay, very good. So, talk about fault-tolerant parsing. And probably the best way to explain what is going on is to do a short demo and then get into the guts of things. So I'm going to go to l1-lab.lamdera.app. L1 is the sort of toy markup language that I use to explore these options, and I'll attempt to go there now. Okay, very good, we are there. So this is the little app, and I can either sign in as guest, or if I have an account, I can sign into that. But I'm going to sign into guest because that's something that you can do if you wish. So there's a welcome screen, and it tells you various things, but all I'm going to do is fetch the public documents that are available. And we're going to take a look at this test document. And as a guest, you are allowed to edit documents, public documents. However, your editing is non-destructive. You can do whatever you want, but your changes will not be saved. So I'm going to type in the sentence that you see in purple up there. So this is a open bracket. Now I've already managed to make a syntax error, and that's because in L1, well, in basic L1, there are just two kinds of things. There's plain text, and there are elements, which are sort of markup items that are delimited by brackets. The first thing inside the brackets is the name of the element, and the rest of it is the so-called body. So the name of this element is red. I notice that as I type it, even though I've made a syntax error, it appears in the rendered text. And then I'll type this very short body, real, and I'll close the bracket, at which point there are no syntax errors. It's rendered in red. Okay, the body is rendered in red. Okay, let's keep typing. Test, and this is math. Now we type $, and once again I have a syntax error because $signs are kind of like brackets. They have to be matched. And then I go ahead and start typing my math, which is the Pythagorean theorem or formula. And notice once again that as I type, it appears in the rendered text, although not so nicely, right? Because it hasn't been rendered as math. But as soon as I type the final $, it is. So but there are a couple of things to notice already. One is that all this is very fast. And the parsing and rendering machine has to be fast in a system like this because the whole point is to be able to parse and render in real time. The other thing to notice is that even though I was making syntax errors in that line, it didn't mess up anything in the text below, this Latin lorem ipsum text. That's because one of the two strategies that I'll talk about for fault-tolerant parsing is chunking. In L1, a chunk is basically a paragraph. It's a bunch of non-empty lines with at least one empty line above and below. And these are the units of parsing. They're all done, chunks are parsed independently, so if you make an error in one, it will not affect the others. I want to do just one other thing in this little demo. Take a look at this source text here, bracket B, bracket blue, etc. In the rendered text, it's this bold, blue, italicized, consectetur adipissum elit, okay? I have no idea how you pronounce Latin, but anyway, I'm going to make some grievous syntax errors by deleting all three right brackets. And you see then three syntax errors signaled in the rendered text. And now I'll show you what happens as I put those back. So one bracket, and you see that consectetur adipissum elit is now italicized. Put another bracket, it's now blue italicized. Put one more, the syntax errors are gone, and now it is bold, blue, italicized text. So once again, the important thing here is that errors be signaled somehow in the rendered text, and that as much of the rendering that is possible to be done is done, and especially you cannot mess up following text. So the question now is, how do we do all this stuff? So let me go back to the slides here, and quick outline. I'll say a few more words about L1. I'll talk very briefly about strategies. We already did one of them, actually, chunking. And the other one is the notion of a text cursor, which turns out to be essentially a form of shift-reduce parsing. And here I want to credit and also give thanks to Matt Griffith, who implemented this idea or came up with this idea in his Elm markup language, and Rob Simmons and his team at brilliant.org, who used this idea in an extremely powerful and versatile parser that they use for their business at brilliant.org. Brilliant.org works in the STEM educational field. I actually did part of one of their courses in quantum mechanics, and it's really top notch, unlike a lot of the digital text offerings available. So, whoops, let's see, there we go. And then I'll do an extended example. We'll see how this text cursor operates, first of all, in the happy path where there are no syntax errors, and then in the more interesting unhappy path where there are syntax errors. So a few words about L1. You've already seen the important stuff, the ordinary text and the elements. There are a few other conveniences. There are certain inline constructs that are rather like what you see in Markdown, backticks for code, $signs for math. You didn't see it, but there are hash marks for top-level headings and subheadings and whatnot. And there are various kinds of blocks. There are verbatim blocks and ordinary blocks. I won't say anything more about them, but they're extremely useful. The abstract syntax tree for L1 is simple because L1 is simple. The fundamental type is element, and it has just 4 variants: text, element, verbatim, and problem. Each of them has a payload. In the case of text, it's string and metadata. Metadata is various things that we don't really have to be concerned with, except that the metadata also has a pair of integers, start and finish, that tell you where that substring occurs in the source text. And that's true of all of the metadata parts that you see below. Element has a name like blue or bold, and its body is a list of elements. So this is a kind of recursive data structure. Verbatim is used for things like code and math. Verbatim type tells you which it is. And then finally, problem is for the kind of syntax errors that Elm parser will discover. Okay, so let's get into the heart of things, which is the text cursor. It's a data structure implemented as a record. One of the fields is the source text. It's just a big string. Another is the scan pointer, which is an integer viewed as an index into the source. And I've indicated 2 possible positions of the scan pointer above in orange and blue. There's a stack, which is a list of augmented strings that are fragments of the source text. And by augmented, I mean that in addition to the actual text, there is a pair of integers indicating once again where this substring is located in the source text. And finally, there is a list of AST values, which I'm just showing you one of them here. I should put brackets around that, I guess, so that you see it as a list. But parens, the fish, is shorthand for what you get when you parse the string, the fish. And you can see why I write it in shorthand, because to write it out longhand is rather cumbersome. Text, quote the fish, metadata, et cetera, et cetera. Now, there are just 2 operations that you can perform on the text cursor. You can shift, which means advance the scan pointer and push the intervening text onto the stack. When you advance, as we'll see, you always advance from where you are to the next bracket or to the end of the string. The other operation is reduce, and that means that you concatenate what's on the stack as a string. You parse the result using Elm parser, and you push it onto parsed and clear the stack. Okay, so of course that begs the question, when can we reduce? And I say, well, we reduce when the stack is reducible. That sounds like a tautology, but there's a technical meaning of this. It's, informally, the stack can be reduced if the brackets are properly balanced. And there's a very simple algorithm for this, but I won't get into that. It's a fun little exercise to figure out what's right. But here are some examples. If the stack consists of just the fish, well, that's balanced because there are no brackets at all. If we have this stack, so there are two elements, each with a left bracket, that is not reducible, okay? And here's another example. There are three things on the stack, one with two with left brackets, one with the right bracket. Oh, no, two with left brackets, and then the final two are right brackets, and that's reducible, okay? So you can think of reducibility as kind of like type checking, because reducibility ensures that the parse will succeed, and type checking assures you that the code can be run without error. So let's take a look at the happy path. So we'll begin with our canonical example. We've initialized the text cursor, so the scan pointer is at the beginning and the stack is empty. And each time we're going to look and we're going to ask ourselves, can we reduce the stack? And if we can, we do so. And if we can't, we shift. And of course, there's a third possibility that neither can be done. And then we have to invoke some error handling strategy. So here we can't reduce, so we shift. We put the fish on the stack. We look at what's on the stack. It is reducible, so we reduce, which means we parse that and we clear the stack. And now we ask, what can we do? Well, the answer is we can shift. So we do that, and once again, put some stuff on the stack. So we'll continue this. I'll sort of go through it a little more quickly now. There's our current state. We look at it. What can we do? We can't reduce, so we shift. We look at it again. What can we do? Well, the stack doesn't look reducible to me, so we shift. We look at it again. Two left brackets, a right bracket, not reducible. We shift. Oh, this is starting to get boring now, but here's our current state. The cursor is at the end of tasty bracket bracket, and that's reducible. So we reduce, and now we're almost done. We once again look at things. Can we reduce? Nope. So we shift. What can we do now? Well, the stack is reducible. There are no brackets at all. So we reduce, and now we're done. The scan pointer is at the end of the source text. The stack is empty, and parsed is a list of AST values, and all is good. Okay? So it remains to consider the unhappy path. So we'll look at this invalid input, and we'll run the machine just like we did before, and we get to the state which I label 7. It's the 7th step. The scan pointer is at the end. The stack is what it is, and it's not reducible. So what to do? Well, we're going to invoke an error handling strategy, which can be summed up by saying we rewind and skip. So let me explain what that means. The first thing we do is we look at what's on the bottom of the stack. So if you look at item 8 there, the bottom of the stack is, well, wait a sec. Did I say this right? Sorry. Yeah, look at number 7. Look at the bottom of the stack. So that's bracket I is. We're going to convert that into a valid AST value. So you see that in number 8, it's element name, quote error, and then the body of that element is a text element whose body is quote bracket I, unquote. Okay, so we take the bottom of the stack, which you see as bracket I is in item 7. We convert it into a valid AST element. And then we do a couple of other things. We clear the stack, and we rewind the pointer, the scan pointer, to the location just after the bottom element. And the reason that we can do that is because we recall that the stack consists not just of text fragments, but of text fragments plus their location in the source text. So the bottom element in the stack has a begin and an end index. So we position the scan pointer right after that. or maybe right at that, I forget. Okay, and then now that we've rewound things, we put the machine in motion once again. And it hums and whirs. And after 8 more steps, we get to the end. The scan pointer is at the end of the source text, the stack is empty, and the list of parsed values is okay. If we scan through it, we see the fish, we see our error element, which you saw in the demo is that highlighted left bracket that says unmatched, whatever it said, okay? But basically the fish still is blue and very tasty today. So, well, that's it. So I'm not sure how many minutes I took. I tried getting this down and down, but let me now figure out how to unshare.
All right, beautiful. Okay, firstly, join me in thanking Jim for his talk. Thank you very much, Jim.
Oh, my pleasure.
Cool. Let's dive into questions. So free for all. Anybody got questions for Jim?
So what about the efficiency of this? Because my naive idea would be that it's constantly parsing the whole thing, or is anything that
yes, it is. That's something I aim to do something about, but first things first. Let me tell you what I plan to do. It's a strategy that I've implemented before in mini LaTeX. So there's a notion of differential parsing and rendering, and that is possible to do because of the chunking. So the idea is you figure out which chunks have been changed, and you only reparse and re-render those. And that, if you have a long document, that's essential. What's really surprising is the document I've been working on is if you go back to that little Lambdera app, there's an article on fault-tolerant parsing, and it's about 3,000 words long. And you'd expect that, reparsing and re-rendering on every character stroke would not work out so well, but it does. So I've been trying to deal with other problems, but I'm definitely going to do this differential parsing and rendering. By the way, let me tell you a story about that. Long ago, before Elm 19, I was working on similar things with mini LaTeX, and it was just way too slow. And oh my goodness, I'm having a lock here. Oh my goodness gracious. Okay, Mario, maybe you can help me. There's this great Elm guy who helped me learn how to do parser combinators. He's the author of JSON update, something like that.
Yes, I think you're speaking about Aaron Wunderhaar.
No, not Aaron. Another one of the greats. Well, it'll come to me. Anyway, he and I were chatting back and forth how to make things better, and I had some bozo strategy that I thought would work. And he said, well, no, you ought to try such and such. And it was basically this idea of differential rendering. And so I implemented it, not in a particularly elegant way, but in a very simple way. And it turns out to work just fine because, see, the idea is that what it does is it figures out, it looks at the text and it figures out the maximal sequence of chunks that have been changed. So if you make a change here and then a change down there, it's going to include all of those things. Not very elegant, and you can do a lot better. But the point is, almost all errors are really errors in one chunk. Like, what you saw me doing. Now, if you make some global search and replace, it's very different. You probably have to just re-render the whole thing anyway. But in any case, this algorithm is very simple and it works really great. It turned out that after Elm 19, everything was so fast that it was almost not needed. But I have it in my back pocket for when it is.
Hi, Jim. I didn't notice if you said, is it a recursive data type that you have?
Yes, it is, because element refers the body of an element. So there are a couple of variants of the element type. One of them is named element, and its body is a list of elements. So yes, it is a recursive type. By the way, one thing I should have mentioned is that the simple strategy that I talked about has the following, there's the following eventuality. It may be that you rewind, you skip and rewind, and then you proceed, but you might encounter another error. And we actually saw that when I was dealing with that Latin text, because I in fact had 3 parse errors. And so the strategy is capable of handling these. I'm a little new at this game, so I don't think that this is the best way of doing things, by the way, but it was kind of a revelation to me, or to use a word that I have learned about, an apocalypse, which means an unveiling, that this is really a shift-reduce parser. And I learned this from Rob Simmons at Brilliant, who is much more skilled in this sort of thing than I am.
Fantastic, thanks, Jim. Any other questions for Jim before we wrap up? Okay, probably a good point to leave it there. So join me once more again in thanking Jim for his talk. Thank you very much, Jim.
Thank you.
Great.